Okay, Bismillahirrahmanirrahim. Beta, today we are starting the next chapter that is current electricity. Beta ji, electricity means the charge and current means the flow. So obviously it means the meaning of current electricity is flow of charge. What is the evidence that current is the electric current is the flow of charge? Beta, sometimes, especially in winters, sometimes we touch a blanket or a door lock or any conducting material and we feel a small shock. And the special when we touch that object again, there is no current or shock again. The second time, usually there is no shock. And what is the scenario in that? Actually, in winters, due to rubbing with any material, we get static electricity. Static electricity means the charge collected on our body, or the charge can be collected on the other. So, better when there is charge collected on our body called as static electricity, we do not feel anything. But what happens when we touch any conducting material? That charge flows from our body or from the other object to our body, and when the charge flows, then we feel the current, the shock. It means the static electricity changes into current electricity when the charge flows. Another example, let's say we are having a battery that is fully charged and is connected with the bulb, but the circuit is not complete. It means the charge, the bulb will be off, the lamp will be off. Why? There is the charge in the battery, but here the charge cannot flow due to that break. And when we complete the circuit, the same circuit, now the charge is on, now the current can flow. Why? What is the difference? Here the charge was not able to flow, but although there was charge in the battery, but here now the charge can flow. It means whenever there will be a flow of charge, there will be an electric current. So electric current comes when the charge flows, and it depends how fast the charge flows and how fast something happens. For that, we use a word rate. Rate means how fast something happens. So the faster the charges flow, the larger the current. So let me just tell you again. Better say electric current, no simple current, because we have studied the convection current in junior classes that there is no electricity, there is flow of heat through the fluids in convection currents. So current only means the flow. So better call electric current in electricity. Technically saying current is not correct. Its full name, its proper name is electric current. But obviously, as we go with the chapter or topic, as we will be knowing already that we are talking about electric current, so sometimes we in quick way we say only current, but uh, obviously then we are talking about electric current, but always use the full name, especially when writing. So it is better to say electric current. So electric current is how fast the charge flows, it depends. So beta, how fast something means rate. So electric current is rate of flow of electric charge. And rate means how fast something happens. And how do we know that something happens fast? So we to find that we divide the material or the quantity by the time. So usually by the time, by from the rate we mean dividing that quantity by the time. So we divide the charge flown by time. The charge is represented by the symbol Q, and the symbol for current is capital I. So capital I is equal to Q over T. And unit for current is ampere, and its symbol is capital A. So if it is asked how much is 1 ampere, so we will use the units of all the quantities in this formula. The unit for charge is coulomb and time is obviously in seconds. It means if 1 coulomb charge is flowing through a conductor in each second, each means 1, then current flowing is 1 ampere. Right, beta ji? Now, although we take the direction of current that it's moving from positive to negative for electron, it is negative to positive, but current is a scalar quantity. Why the current is a scalar quantity? Although we discuss its direction, like why it does not obey the vector rule. Current has a direction, but still it is taken to be a scalar quantity because it does not obey the vector rule. What do you mean by vector rules? The head to tail rule or the parallelogram rule. These are the vector rules. And what are the examples? Consider we are having two equal and opposite forces acting on an object. So we get the resultant to be zero. But whenever on same point, two opposite current enter, rather than they cancel out each other, they actually add up. If we are having another alternate path to flow, this tells the being opposite direction of the current is not having any effect. Although they are opposite to each other, but still they are adding up. The forces never do, the vectors never do this. So this is why the current is scalar quantity. Although it has a direction, there can be a question: 20 milliampere current flows through a conductor for 8 minutes. Find the charge. So we can use formula I is equal to Q over D. Charge is Q, can be Q is equal to IT. You can see the formula, and milli means dividing by 1000, right? And minutes are to be converted into second by multiplying by. But usually when we say electric current is flowing through a conductor, it is the electrons which are flowing through the conductor. So there is now one thing which I would like to discuss with you, that is quantization of charge. What I'm going to discuss is quantization of charge. What does that mean? Beta, we get the charge on any object stored when it loses or gains electrons, right? So it means quantization of charge means the charge on any object, like you buy uh, a large number of chocolates and you have to find the total cost. How do you find? You count the number of chocolates and multiply by cost of one chocolate. Similarly, beta, charge flown or charge stored on any object is equal to number of electrons it has gained or lost. Multiply the number of electrons with the charge on one electron. You get the total charge stored or flown, right? So, beta, What is, how do you write it? The total charge is represented by a symbol capital Q. Number of electrons gained or lost are represented by capital N, not a small n. Keep this in mind, capital N. And the charge on an electron is represented by small e. That is also called as elementary charge, right? And the value of elementary charge is, this elementary charge is given in the data, and it is equal to 1.6 10 raised to power minus 19 coulomb. Right, Vita? So from this now, I would like you to know we had the formula of current I is equal to Q over T. Then there can be another formula for current, that charge on any object could be, or the charge flowed with the charge which had flowed can be number of electron flowed multiplied by charge on one electron divided by time. So beta, there can be two formulas for the current, electric current. One is charge over time. The another is number of electrons times E, Ne over T, where N is the number of electrons flown in and out through a conductor or through a conductor, and E is the charge on one electron, which is also called as elementary charge, right? So beta, if it is asked that during this time and carrying this much current, how much, how many the charge have flowed, or how many electrons have flowed through the conductor. If it is asked, if we have to find the number of electrons which have flowed through, so which formula you are going to use? That will be I is equal to Ne over T. So to find, you have to find this, and now the current is given. The current is given to be 20 milliampere, which you milli means dividing by 1000 like this, and time 8 minutes is converted into second multiplied by 60, and the value of E is elementary charge, which I have written here and here. So you substitute the value of E, I, and time. You can find the number of electrons, right? Clear?
Yes,
Yes.
sir.
Okay. Now, beta ji, there are some questions. Let me tell you, this number of electrons, what we were talking about, that must be a whole number. The whole number is called said to be an integer. Like when if you are to count the number of people entering a building, so you will always tell it as a whole number, not in decimal. So that number must be an integer. So what is the formula for quantization of charge? That Q is equal to Ne, where N is an integer, a whole number. So beta, sometimes coming back to Q is equal to Ne, can this can be rearranged like that. So whenever we divide the charge on any object by the charge of electron or elementary charge, the answer must be an integer, the whole number, right? For example, we were given 1, 2, 3, and 4 different amount of charges, and it is asked which of these can be a possible charge on any object. How would we know? We will divide the charge on any object by the elementary charge, charge of electron. We are using this and see what the answer is. And we divide this all four times. All the charges are divided by the elementary charge and we see the answer. And look, these three answers, they are whole numbers. This one, this one, and this one. Means these charges are possible that uh, which can be stored on any object. But when the answer is not a whole number, this means this charge is never possible to be stored on any object. Only charges are stored on any object when it loses or gains number of electrons. So the charge object is always an integral multiple of charge of electron, right? Integral multiple means if you divide the charge on any object by the charge of electron or elementary charge, the answer must be an a whole number integer. If the answer is like this, if the answer is like not in a whole number, is not possible on any object. Clear? And on any object, only those charges are possible on any object which are integral multiple of charge of electron. Or when the charge divided by the charge of electron or elementary charge, the answer is a whole number. This is called quantization of charge. So here, the summary of this is the formula for current. We are having two formulas. We have another other than these two. What are those? The first formula for electric current is charge flowed divided by time, or Ne over T, where N is the number of electrons flowed and E is the elementary charge or charge on one electron, and T is the time for during which these electron or charge had flowed, right? So two formulas for current are electric current are I is equal to Q over T or Ne over T. N is to be capital because small n is another specific term which are totally we are going to discuss. Now coming to this, Beta ji, usually we say the current can flow through the conductor. Why? What is that only the conductors? So, but like I on the chair, the lower part of the chair is made up of metal. It has three electrons, but there is no current in it. Like our gate, the body of our car is made up of metal which have three electrons, but there are no current in those uh, metallic parts, although they have free electrons. But the reason is the free electrons in them, they are moving randomly here and there. They are not moving in one same direction, so they cancel out each other's effect. Like at time in a class, five or six students try to explain something loudly. So actually, they won't be able to understand the student because their sound will be cancelling out each other's effect. So beta, whenever when is there a current in a conductor? When the conductor is connected with a battery, and what is special? That every battery has a positive and negative term. So what happens? Then electrons are moving from negative terminals to the positive terminal. So all the electrons are negatively charged now when connected with the battery. then all the electrons have one same direction. So then when they move in one same direction, then electric current is formed. And one thing you have to keep it in mind that when current flows through a wire, after using an electric circuit or wire for many years, more than 10 years, 20 years, but the number of electrons in the wire stay the same. The reason number of electrons entering is equal to number of electrons leaving the conductor. This is a simple, you can say, uh, replica of the Kirchhoff's first. So, beta, in any conductor, why the conductor never runs short of electrons? It never loses its electrons actually. It gains some electrons and it loses the same number of electrons. So its number of electrons always stay the same, right? Clear? And one thing, there is another concept. We say conductors, matters are very good conductors. And why current can flow very fast? And we think the current is lightning fast, but in actual that is not the case. The speed of electrons or free charges inside any conductor is called the drift velocity, and that is really, really slow, like 1 millimeter per second. It is an example. In fact, the speeds can be even slower than this. Then why it happens that we switch on and the light switch on a lamp at our home in domestic circuitry, the bulb lights up the same time. Within a second, it lights up. It tells the speed of electron is lightning fast. Actually, it's not. The speed is really slow. In fact, there is a stream of electron, and answer is the same effect. We say the number of electron entering is equal to number of electrons leaving. So when right away one electron enters, there is a push to the line of electron, and the electron for this end leaves the conductor to the lamp or the appliance. So the appliance receives the electron from this end actually. The electron has entered from this end. This electron reaching from this to right side will take a lot of time. But the push of that electron will make the electron at this end to enter the appliance. So the appliance receives the current, you can say, exact the same time, simultaneously. As we switch, the electron enter, the electron leaves from this end as well, right? Now, there is an important formula that can be the last point for today, and that is, so we say a conductors, metals are good conductors because they have free moving electrons. So there are different type of conductors. Not all the metals are equally good conductors. Some are better than others, and the difference is free electrons. The ones which are having larger number of free electrons are better conductors. So for that now we have a term or symbol, the small n, which is called as free electrons or free charge density. Number of free electrons or number of free charge density is called as n. Like this is a very important term. The small n said to be number of free electrons or number of free charge density, and as like a normal, the n, the number of free charges or free electron density is equal to number of free charges or free electrons divided by the volume, right? Now we are going to do a very important derivation. So small n is number of free electrons or number of free charges per unit divided by volume, and number do not have any unit, and the unit for volume is meter cube. So this gives the unit for number of free charge density or N to be the meter cube is in the denominator 1 over meter cube, which we read as per meter cube, and it also can be written as m raised to power minus 3. Depends upon you. How do you like to write it? So, beta, what do you mean by small n? Small n is number of free electrons or number of free charges density, right? So, beta, its formula is number of free charges or number of free electrons per unit volume divided by volume. Let's say, consider here we are having a wire, a conductor, which has a length L and its area of cross section is A. So wire is like a cylinder, cylindrical. It is cylindrical in form. So the volume of cylinder is area of cross section multiplied by the length. And free charge carrier density is represented by small n. So beta, that volume AL dividing will multiply with n. And what do you get? We get number of free electrons or charges in a conductor is equal to NaL, right? Small n is number of free charges or electrons per unit volume divided by volume. And if the cross section area of the volume wire is A and it has a length of L, and as the wire is cylindrical in form, the volume of a cylinder is area of cross section multiplied by its length. So A times L will give us the formula of volume. So volume can be written as AL. Then AL dividing will multiply with N, and we get the formula for number of charges of free electron. Right? So beta, as we have formula for basic formula for movement is equal to charge over time. This Q is the total charge which had flowed during this time. So beta, when we say now the charge has flowed through a conductor, the charge is not one single object. It is made up of a large number of small electrons or free charges. So it means that in that charge, the number, a large electron free charges have flown. This is the formula for the total charge, similar as you were having the total cost of chocolate. You count the number of chocolates and it with chocolate. Similarly, if charge that flowed, we will multiply charges with two as just we did now find free charges, number of electrons in a cylindrical wire there and a this value this value here and multiply it with the charge on one electron. What happens? We substitute this value here, the number of as number of charges, number of electron, and multiply it with the charge on one electron. So we get the total charge which had flown is through the conductor. It's just like number of chocolates multiplied by cost of one chocolate. So beta, this gives you the total charge. And when we place this value of total charge here, substitute here. So now we get formula I is equal to NaL over NaLe over T. Now this formula can be rearranged like we can separate L over T from others and all other quantities N, A, and E are written separately. So, beta, L is the distance divided by time. We just rearranged it. We write NA as it is here, E here, but we just write L over T separately. Why? L is the length, and length is the distance divided by time, give you the speed, V. So, beta, distance divided by time is written see, as small v, and that is speed of free electrons, which is named as drift velocity of free charges or electrons. Clear, beta ji? I hope you can understand. So, this is the most important formula of electric current we do in A level. It has many questions related to that. Now, uh, what is so special about that? That in this formula, I is equal to NAVE. V is the drift velocity. And let me tell you, if we are considering the electrons to be flowing through the conductor, then we use the charge with the symbol E. But if we say a free charges, some other free charges Q is flowing, small q, then E can be replaced by Q, but both represent free charges, right? Clear? So formula sometimes is written as NAVE, or the E can be replaced by Q sometimes as well. Both are correct. Both are the same form. Now, interesting point. The from this formula, if we make V as the subject, the NAE multiplying will divide here. So we observe two things. V and N are having inverse proportion. Inverse, inverse proportion relation. What do you mean by that? The larger the value of N, the slower will be the speed. But wait a minute. What do you mean by larger value N? The N small n. It's not capital N. Let me tell you. Small n is number of free charges or number of free electrons per unit volume. Capital N only number of electrons or charges. This is per unit volume. Beta, when we say na, a conductor having a larger N, it means it has more free electrons, more free charges. And when we say a conductor is having a larger number of free electrons, it is a better conductor. But in junior classes, or let's say before this class, we used to the better conductor will have the speed of current. Let the current go more easily, more faster. But reality is different. The better the conductor, the larger the value of n, the slower is the speed of electron. But what we observe is through the current flows very fast. Actually, they have more electrons, and again the reason is this one: the number of electrons which enter from this side. If one electron enter, one electron leaves immediately from this side. As there will be more electrons entering in a better conductor, the more electrons will be leaving. So that makes the current to be larger in a better conductor. But the speed of electron is slower in better conductors. In bad conductors, they are faster, right? And the other point, B is also inversely proportional to area of cross section. B, if we are having a conductor wire which is thicker on one side and narrow on the other side, the where the wire is wider, right? It has greater diameter, the speed will be slower. And where the wire is narrower, lesser, having lesser area, the speed is fast. So this again now is against our daily life logic. Right? Like we are having a wider road where traffic flows faster, and on a narrower road, the traffic slower. But it's opposite here. So there is a simile. If you have watered plants by using a pipe, plastic pipe, n- nylon pipe, you would have observed it. If you make the opening of the pipe narrow, isn't the speed of water faster? And when you relax the opening of the pipe, it gets wider, it's slower. It's very close to that, right? And there is another point which I would like to, that usually the wires are the roundish at the side, and roundish means the area of cross section can be a formula pi r square. So this tells area is proportional to square of radius. So we have discussed in deformation. When we say area is proportional to square of radius, means whatever happens to the radius, its square time happens to the area. Means if you multiply area by 2, radius by 2, the square of 2 will multiply with area. Means similarly, if you multiply 3 with the radius, the area will be multiplied square of 3 9 times. Similarly, if you divide the radius by 3, the area will also be divided by, but by the square of that. Right? Clear? I hope you can understand that.
Yes, sir.
Okay,
Yes,
beta
sir.
ji, that is all for today's lesson. Any question, then you can ask.
No, sir.
Ji Sarosh, is it fine?
Dreadful,